Welcome to the colloquium. Today, I'm going to talk about how to efficient use a single CPU to train a neural network. GPU has become the de facto standard device for training neural networks. This is because training with GPUs is much faster than training with CPUs. And many people believe that the two major factors behind the success of AI are big data and the GPU. GPU, especially modern GPU, make it possible to train a large scale neural network over large data. So today, so most people, although most people know GPU is the right device to use to train neural networks, but some people are not so sure whether he or she needs a single CPU or multiple GPUs. So the simple answer is, in most cases, if your neural network are small or medium size, a single GPU is sufficient. Only for some very large models like the larger language models or some other very large neural networks, in those cases you need multiple GPUs. And it's not always true that more GPU, the better. If for a small or medium-sized neural networks, training with more GPU can not do any good, but just the opposite will actually will reduce the performance. I will show that later. So the choice of whether we should use single or multiple GPUs depends on the workload, or to be more specifically, the size of neural network, the size of the data, and also what type of GPU you are going to use. Because we have different type of GPUs from P100 to the latest one like A100, H100. So I think the trend is the newer GPUs are more and more powerful than the old ones. So if for the workload, your GPU is hard to catch up, then you can consider using multiple GPUs. But if in some other case, if your workload is fairly small and can be easily handled by a single GPU, in this case, the GPU is underutilized. So this is the issue that I'm going to address in this topic. So what we are gonna do is we're gonna, increase the load as a result to increase the throughput. So to fully utilize the GPU capability. I will show you how to do that, but the first question is, how could I know, whether I should use a single or multiple GPU, whether my workload is should big or small? First, you make a compare of the scale of your network with something similar. I see some chat there to see if anything. Okay, that's good. So if some other similar neural network use a single GPU, it's more likely you don't need multiple GPU at all. The second method is you do some experiment. You can try on single GPU, either with different type of GPU from the lowest one like T100, P100 to the advanced one like A100. You can check to see how the training speed is. You can also try multiple GPU to see if that helps. So that will give you some sense whether or not you need a single or more GPUs. You can use NVIDIA SMI to monitor the usage of the GPU, and that also can give you a sense whether it is fully utilized. But depending on that is not sufficient. I will show what happens in the example later on. So here I list the table that I copied from our wiki page. From this year rack application, we ask applicants to specify the GPU request based on a specific units we called RGU, reference GPU units. Basically, from the table, we can see that A100 with 40 gig memory is roughly equivalent to 4 P100 GPUs. So that's something that you can give you a sense, a ballpark figure of the powers, the different powers of different GPUs. So let's go back to our focus of today. So what we should do if we know that a single GPU is not fully utilized. The simple answer is just like the boy, we can give, instead of giving him one box, we give them 4 boxes. So so something like that. So in training, in deep learning training, which means that we are gonna run multiple training processes on a single CPU in parallel. So probably someone will ask why we need to run training multiple times. If I design or build a neural network, I only need to train only once to get the model. It is true theoretically, but in practice, you will never get the optimal model with just one training. This is because you need to tune the hyperparameters, you need to choose different learning rate, batch size, and you also sometimes you need to change a little bit of the neural network. For example, add a new layer or remove a layer, or you can compare different size of kernels in the convolutional layers, something like that, to see which one can give you the best model. And in that sense, you need to train a neural network with similar architecture, with different hyperparameters multiple times in order to find the optimal one that can give you the best performance in terms of either classification rate or recognition rate or whatever criteria you're gonna use, okay? So you need to run a training process not just once, you need to run multiple times. So here we are gonna run a training instance, not just one, maybe multiple training instances on a single CPU simultaneously. So that's how we expect that could saturate the GPU so that the GPU is fully utilized. That's the basic idea. So there's two ways. One way is we run multiple instances on a single GPU without doing anything, just run on a simple GPU. The second one is we first split a GPU into multiple logical GPUs and then run one training instance on each logical GPU. So based on my experiment, the second method give me a slightly better result. I will show the result later on. So yeah, so for most people, probably you are not aware there are some concept like a physical or logical GPU. So you only know GPUs are GPUs. But in fact, TensorFlow deal with only logical GPUs. And but by default, our logical GPU is created out of a single physical GPU. So that's why you are not aware of logical or physical, whatever. But the concept is that it is possible that you can split a GPU into multiple logical GPUs. So that's something that we are going to do in our experiment. So here are some functions that I'm going to use. The first one to list the available GPU devices. The second one will list the logical GPU devices available to TensorFlow. By the way, I'm using TensorFlow, not PyTorch. I assume that PyTorch will have a similar function calls, but I'm not quite familiar with that. The third function, set logical device configuration, will split a physical device into multiple logical GPU based on the configuration that is passed into this function. I will show how to use this one later on, okay? And in the experiment, I'm gonna use two neural networks. One is the smaller one, the other is medium size, and I'm gonna run experiment actually you can consider I run 3 experiments. The first one, just regular one, I run a single training session on a single GPU. And the second experiment, I'm gonna run a multiple training instances in parallel on a single GPU without doing anything fancy, like splitting it into logical without. But the third one, I'm going first to split to multiple GPUs, then run multiple training processes. That's the 3 experiments. So before we take the code, let's just have a look of the overall structure. Basically, I'm gonna build the neural network and also loading data and start training in this file. To train in this file, I train the handwritten digital recognition using the MNIST dataset. And then I'm using this one, basically the baseline, just call this function, just run a single training process on a single GPU to get a baseline timing. And then I would do, run multiple training sessions, processes on a single GPU, also using this as a base function call. So this one called a function inside this Python file. The third one, I split, as I mentioned, I split the GPU and then run it. For the second, I used the ResNet 50 as the neural network. Basically, I will do the same experiment over baseline, no split, and split test. So let's take a look of the result, the code first, then I run it. All right, so here, probably I do this one. I have, this is the ResNet, this is the small neural network. So you can see here, I have a function called build CNN. Basically, I build, it's very short. Basically, I build first a convolutional layer, and then followed by a max pooling. Then I flatten it and connect with a dense layer and drop out and another dense layer. That's it. So very simple, very small neural network. And yes, I think number of field kernel size. Okay, so the kernel size is 5 by 5. That's something I need to mention. That's it, I think. Yeah, that's it. So once we build the neural network, we return the model. One thing that I need to mention that I put the building process under the scope of with device GPU. The GPU is past the device. Later on, I will pass the logical GPU here. And yeah, so that means I want the following layer, the operations will be calculated or operated or executed with GPU, not a CPU. All right, so next major function is called mnist_CNN. So first I call the build function that I just described. And then I load the data and I do some mapping. I think this is optional, but I do it, I basically optional, I just normalize the data because by default, the data is, the data range is from 0 to 255. I squeeze that range into, let me see, 0 to 1 and convert it to a float. Okay. So basically, I call a mapping function. Basically, I call this normalized function. And after that, I batch it, create a batch. Basically, later on, I can use training as a data set. It's already batched. And I want to cache it. That means the data that the first time I loaded it, read it in from file will keep in cache. So the second, in the second epoch of training, I do not need to load from file again. But not necessarily, it depends on, sometimes if the memory is enough to hold the data, yeah, we don't need to read from file. But if it's a very large data file, TensorFlow will create a so-called cache file, okay? And then prefetch, that means that to make the the data I/O more efficiently. So that means when I processing the current batch, it will prepare the next batch in parallel. So it will get it ready, when its time comes. And lastly, I do fit to do the training. I want to do this amount of training. The number could be 50 or 5, depend for the smaller one network. I use 50. For the ResNet, I use 5 epochs, so something like that. And I do the timing. I take the time before training. I take the time after training. I do the minus to get my time used just for training for this session. Okay. So this is my code, the baseline, the fundamental module. Let's see how do the baseline. This one. Let's take a look. So it's very short. Basically, I get the physical device, physical GPU list, because I only have one GPU. I only have one. I only use 0 index, the first one. It only has one element there. So by setting memory growth to be true, that means I don't want the algorithm occupy all the GPU memory, and only allocate the memory needed for running the training. Define learning rate, batch size, epochs, so on and so forth. Then I'm gonna run this one. So that's something that I'm gonna use. Probably I at this point I can do I change it a little bit, baseline. So first of all, I'm gonna run the I'm gonna use the smaller neural network, not the big one. Secondly, I'm gonna run it 50 epochs. All right. I already allocated interactive session. Where is it? I think I did somewhere here or already here. Okay, here. I use this slog command, request a P100 GPU, and yeah, that's it. So I'm gonna, because I'm already here, you can see I can run it as a batch. So for example, here is a job script that I'm gonna run baseline twice, just to get the average. Then I run either the split or non-split version. The parameter followed, the argument is the number of training processes that I want to run simultaneously, 3, 5, 8 until 55. That's the structure. All right. So I'm gonna log on to, I use another terminal to log on to the GPU node. Yeah. So if I use NVIDIA SMI to check, you see I have P100. The utilization is 0% because I haven't run anything yet. So now I'm gonna run a training Python around the baseline. All right. So here I can show the performance. You still see 0 because it's in the data loading session. I think it hasn't started yet. So just wait, and it's loading data. It's okay. Now you can see some number here, but the best way is to watch it. So that means I can get that I want to see an update every 1 second. I see, 70, 60, 70, something, 70, 63, 60. Yeah. So you see, it's not fully utilized, even when the training is in the full swing. It's not fully utilized. So that means there are rooms for me to, to increase the load so that I can get a better throughput. Also, from the memory, you can have, it has a 12 gigabyte. Oh, it's finished. But before that, you can see the number is like 4 gig or something. I forgot the number, or maybe even smaller than that. All right, so here I can see it's finished. So it gives me a timing 66. But if you run it again, you give a slightly different number because there's some small, variations always there. And if you run the, sorry, probably not this one. On this side, probably. I'm gonna stop this one. Oh, yeah, I run on this side. Let's edit it a little bit. This time I'm gonna run the other one using the other which is ResNet. I'm gonna run 5 epochs because it's more time consuming. Let's run it. And let's watch it again. Oh, now you can see the memory is increasing, but that means that the data loading and probably the model is loading into the GPU as well. But okay, I think it's loading now you can see some number there. Still not. Okay. 12. I think still not in full swing yet. Okay, you see 80, 90. It's larger than before. Than the MNIST small neural network, but still is not fully utilized. Let's see this side. Yeah, it's not fully utilized. So now we can look at the, let's stop this one. Probably we don't need to stop that, but let it run. But I exit the from the GPU node. And let's take a quick look of the no split, simple one, just run multiple instances. How do I do that? So basically, the first one is you can just set the memory growth things. This one. So first, I take the argument and interpret it as a number of training sessions that I want to run. So here I use thread. So the number of training sessions or training instances is also the number of threads I'm gonna create. And after that, I'm gonna get the logic GPU because I didn't split it. So I only get one in the list. And now I'm gonna do a for loop over the number of threads. So I first create a learning rate, then batch size. You can see I just create random numbers around the true around the original one that I think. But for you, probably you should do something similar to grid search, which means you go over a number of options for learnings, either linear or in log scale. Change from the smaller one to the larger one. So also for the batch size, you do the same thing. But here I just do experiment. I just generate some random disturbance around the number that I want to use. For example, batch size 256. I just generate some random number there. And then I spawn a thread, and I'm calling the MNIST that I imported either from the first neural network or the second network. By the way, I'm using the same name for the ResNet. I shouldn't, but I just lazy, just use the same name. This is the one that contains everything from neural network building, data loading until final fitting, final training. It's all there. So you only need to pass the argument to this function, like the the logic GPU name, learning rate, batch size, epoch. That's all. It will start a thread running this function. You can see here in the for loop, I always use the same logic GPU name, which is like I said, I want there's because I didn't split it. There's only one logic GPU, so it's always 0. After that, I start the thread, and that's it. And the join part is not very necessary, which basically the join is block the execution of the main thread from going further. It's not very necessary in this case, but anyway, this is the no split version. Let's take a look of the last version, which is split. How did I do it? The same thing, I get the number of threads or also the number of training instances that I'm going to create. This part, I got the memory, the total memory available. Because here, for P100, I require the smaller P1, which is 12 gigabyte. But for V100, I could get either 16 gigabyte or 32 gigabyte. So I inquiry about the size. Once I have the size, I divided the size by, I think the GPU has to reserve something internally, like a controls the whole process. Then I divided by the threads to get the GPU size for each logical one. And once we got the memory for each logical GPU, I can use that to create logical GPU. So here is what I do. I do a for loop. Before that, I have an empty list. I'm going to add each of the configuration into the list. And inside the list, what I add is this one. So I use a logical device configuration call, and the argument, I only limited the memory, not exceeding this one. So that's what I did. And once I have a list of logical configurations for logical GPUs, I can call this function to create logical GPUs. Or in other words, I split the physical memory into multiple GPUs based on the configurations. So you see GPU 0. So where is it? The GPU that I got here, it's a physical GPUs. Because I only ask one GPU when I do the selloc, so I only have one physical GPU. So now if I use this function to retrieve the logical GPUs, I have multiple GPUs here. So this is a list. I can print it to see how many GPUs I have. All right, so up to this point, I already split the a single GPU into multiple ones. I'm gonna run a for loop again, but this time I'm gonna start the thread, and here I use the GPU name. Here the GPU, I do a for loop. Have you ever know the enumerate? So I loop through this list. The first one gives me the index. The second one gives the element in the list. So loop through the element. So the seventh one is the logical GPU. And here I got the logical GPU name. So the same thing, the similar structure. So I already run them and I already got the result. You can see that for example, for P100, I got something like this. This is my print. Time used something like this. And some garbage information I'm not interested. And the second one, and time for 3 logic GPU, the same thing. And you can see, the learning rate. And this is something that timing use 3 threads and so on and so forth. And you can see the information here. So an easy way to get the result, because I'm only interested in timing. So I grab time. So from the input, I just grab those that I'm interested in, something like this. I can get the time. You can see for the baseline, I got 122 if I run three training processes in parallel, I got a total training time like 245, and divided by 3, I can get the average that per training session. So that means for this one, 3, about 70 something, 78 or 70 something is smaller than 122. So that's how I do. So let's go back to my slides. Let's take a look of the result. So here, first I do a test between no split and split, no split, and I use the smaller MNIST neural network on P100. You can see that the split has a better performance. And the next experiment is I use different type of GPUs, and I also use the smaller neural network. And you know that we have A100 on Narwhal. I haven't done a test on Narwhal, but I can do a test. If I did on A100, I expect to see a curve somewhere from here and even lower, because the A100 is much better than the previous GPUs. So you can see that the general trend is, if I run with just one instances, for example, for the T4, I got something like 70 something, like 72 or 73 something. And then if I use if I run 3 training instance, I got like 51 per training session. But then gradually it will hit plateau. In general, around this is 5, this is 8. I think around 8, you hit plateau. Once you increase the number of training processes, you won't gain anything. Sometimes even worse. Later on, I will show the result. This is the result I'm showing using the ResNet 50. You can see in the very beginning it drop off. If I increase the training number of training instances, I think somewhere around 5 for the smaller one, 8 for the larger one. If I keep increasing the training instances in parallel, it gets worse. And it failed when I increase even more. I think at that point, it go beyond the memory. I got out of memory issues. So that's the result. So at this point, I asked myself, is there a better way to increase the throughput other than running multiple instances in parallel? How about we use the mirrored strategy? We already know how to split a physical GPU into multiple logical GPUs. But if you think it twice, it won't help. The reason is, for mirror strategy, you basically you split your batch data into multiple slices and fed them into each logical GPUs like this. And each logical GPU basically does is to calculate the gradient for those training parameters. Once you got the gradient from each training, let's say GPUs, you will do combine them together, basically do the average, and use the average gradient to apply your to update your training variables. And then you use the training variables to update the model again and do that's just one training iteration. You will do it over and over again. Why it doesn't help? Basically, if a single GPU is sufficient enough to handle a batch of training data, what's the point to split the batch data and split the GPU? You won't get any better. But the only thing you can get is some overhead. You need to do some actual work to split and to combine. So and also to update the thing, the mirrored to propagate the mirrored update across the multiple instances. It won't help. I actually did a test before. Instead of split a single GPU into multiple GPU, I actually use multiple physical GPUs without splitting anyone. So I did it on P100. You can see I use a fixed batch size, run fixed iterations. If I use one GPU, one P100, I used 135 seconds. But if I use two CPU, I need even more time. The same thing for V100. Here I plotted here. The more GPUs I use, the longer time it takes. So it won't help. All right. So let's just quickly summarize what we have learned from this experiment. So first of all, if GPU is underutilized, we can well, first of all, we can use use this NVIDIA SMI to find whether or not the GPU is underutilized. We can also do a test. And if we find it is the case, it's not fully utilized, we can get better throughput by simultaneously running multiple training instances on a single GPU. And we found that the split option is better than non-split. So that's it. So that's all for today. Thank you so much for attending.